So anyway, I think you're probably all pretty well prepared, so I think we'll just go ahead and have the exam today, okay? No, kidding. We'll do review today and then exam on Wednesday. But there's a number of things that we can do for review. We can look at different problems, different outlines and things. But are there any questions about any particular problem? Yeah.
Yeah, it was number 4 on the test from April 18th.
Okay.
I looked over your solutions, but I still didn't understand
Sure.
what we
All right. So yeah, we can look at that. So. So this one looks like so that number 4 for thing was kind of the sign test. It's a little bit different, actually. I guess I didn't catch that. We talked about the sign test as an alternative briefly, but I don't actually plan to put that on. So it's a good one to discuss, so we can discuss what it would be like. Right, so this one said there's an experiment done by mail order company, color of advertisements, right? And so the catalogs were sent with either 4 colors or in grayscale. There are 10 different departments, and they record their advertising. And 9 out of 10, the sales were greater. So let's say that it's not, that number. Let's say that there were 9 out of 10. Let's say there were, 100 different, markets. So by markets, I mean little geographical things, kind of like teacher state or something like that. And then greater than the 4 color ads were used. And so some of them got the color ads and some didn't. There's 90 of the, and then let's say that 90 of them, it's more sales when the color ads were used. Right? And it doesn't really make sense to test whether there's a significant effect because we so strong, but we could, right? Does color have a significant effect on sales? So a P of 1/2 would, 50% more for color, 50% more for black and white would be neutral, no effect. So we could test, at the core of this is testing a hypothesis, is the proportion 1/2 or not, versus an alternative, maybe that P is bigger than 1/2. You could write it as just not equal to 1/2 for the purposes of the exam. You could write one-sided or two-sided. If it seems like it should be one-sided, you can do it that way. Otherwise, by default, just do that. Right? So it's 100 markets. So we have an N. It's counting this. The proportion of markets where color is better, 90 out of 100 is 0.9. And so we want to do this hypothesis test. So for the proportions, we calculate a z-statistic. We do p hat minus p0. This is our value of p0 in this case, divided by standard error. And the proportions one had a p, 1 minus p over n. And we put in the p0 value under our null hypothesis. Square root of all that. So this would be 0.9 minus 0.5. And then we had 0.5, 1 minus 0.5 over 100 in there. So 0.4 over, now 0.5 times 1 minus 0.5 squared, so the square root of that is 0.5. And that 100 in the denominator would come up here, and so there'd be a 10 up here. So this is 4/5 times 10, or 8, would be our z-value. And if we're doing a 5% test, alpha equal 0.05, significance level, where we're going to reject H0 if our statistic is greater than 1.96, or if we do it one-sided, right, then it's about 645, right, for one-sided level at a 5% significance. But in any case, 8 is huge. And so because of that, because our z value is 8, we reject the null hypothesis, and it's not equal chances, equal benefit from color, or the color's doing a lot better in terms of sales. The way it did it in that solutions is just it only had 10, so it added up the binomial probability 10 plus probability 9 to calculate the tail area. Yeah.
Where'd you get that P is that the P equals 1/2?
Mhm.
Like, why wouldn't you be using the 0.9?
So it's so they're doing this experiment in the market to say, is it better to use color or not? And so the null hypothesis is no change, no difference, no benefit is going to be 50-50.
Okay. And so is that like standard pretty much for each
Pretty
process?
much, yeah, something like that. And then the sample proportion, based on the data, is going to be this p hat value
Okay.
at 0.9. So that's more how this one would be. The other variation in this type of problem is maybe do a 95% confidence interval for P. Now, P is the probability that color and the color ads have more sales, has more sales. And the black and white ones. So it's a sample, so we have n equals 100, and we had 90, so p hat was 0.9. So 95% confidence interval for the portion is p hat. 95% for confidence intervals, we use a z of 1.96. 1.96 p hat, 1 minus p hat, n. The p times 1 minus p over n is like the other formula, but we put a sample one in here because there's no null hypothesis or confidence interval. We just where it's what's likely. So 0.9 plus or minus 1.96. 0.9 is p hat. 1 minus that is 0.1 over 100. And this one actually, with the square root, you can take the square root of the numerator and square root of the denominator. So square root of 100 is 10. 0.9 times 0.1 is 0.09. The square root of that is actually 0.3. So this is actually 0.3 out here. So 0.03 is about 2 times that. So it's something like 0.96 down to 0.84. It might not be exactly that the numbers, it might be off by up just a bit, but that's about what it is for a 95% confidence interval. Right? We generally want to make sure that n times p and n times 1 minus p is greater than 10. It qualifies in this case, right? If I could have a follow-up part C. Would you want to use this kind of normal confidence interval if we only had 10 trials? Probably not, right? Because it's not very discrete. It's a normal approximation to the binomial doesn't work so well if you have a real small sample size. This is a margin of error of about 0.06. What if you wanted a margin of error of 0.04? Proportions, we also did a sample size. We had a sample size formula, which was like this for this one. The z is 1.96 squared. Put that in there. Now sometimes we use 0.5. You could put 0.5 there. That's a conservative thing to do. But if we had this initial survey that said it was 0.9, you could put that one in there. And if the margin is plus or minus 0.04, we put 0.04 in here. And that'll give us some sample size. Yeah?
I kind of had a question about the margin of error. There's another question. I think it's like 3C on that, or 3V on that same test. And you're doing that same thing, like trying to calculate.
Get a sample size, yeah.
Yeah. But how do you know whether to use p hat or p naught in that margin of error? Because here you did 3 different examples, one using 0.01, 0.015, and 0.5.
Yeah.
But in the example, the p hat was 0.015. So
Oh,
why wouldn't you just,
0.015, and so.
so why wouldn't you just put in 0.015? And why did you do 0.01?
Yeah, so it's a, if you use a reasonable number for the exam to put in there, that'll be fine, and it would be a reasonable interpretation.
Okay.
So the choice between those three things in there, it's, you know, the using 0.01. So in, show everybody this thing. So these are the, so page 3. This is government buying combat boots, and they're only going to, they have to have less than 1% of the pairs defective to qualify as a good shipment. If they ship too much, the government's going to say, I'm sorry, these aren't any good, you have to take them all back. So they sample 1,000 pairs, maybe out of 1 million or something, and 15 of those pairs are judged to be defective. And have they, you know, that's a little bit more than 1%, right? The p hat is 0.015. Are they in fact not at 1% defective, which is the manufacturing line? So it's testing versus 1%. So here is the, it doesn't say either, well, it says either hypothesis or confidence interval could be used to check is 1% reasonable, right? So if you do a confidence interval, we do the confidence interval, and it includes 1%, so 1% is possible. If you do the hypothesis test, it comes out this way. We get a z-value of 1.59, which is not so extreme, so we don't project. And then it follows up what sample size. You want the 95% confidence interval to be a margin of error of 1%. This 1%, right, is the thing in the denominator. Right, the margin of 0.01 is there. And then you need, well, 95% is 1.96. We need p, 1 minus p. So if the government standard is 1%, you know, you could say, well, you know, I'm going to put 1% for that for planning. Assuming the company is honest and is 1%, that would be a good planning value. But they've done the sample, and in the sample they got 0.015. So, you know, if you had that sample value from like a preliminary one, you might put that in. The very conservative thing that gives the biggest value is to put in 0.5. So if you don't know anything, you probably start with 0.5. So once you have a pretty good idea of the subject area, you could replace it with something a little bit more reasonable. And it, yeah, when it's that extreme, the p times 1 minus p is quite a bit smaller than this one, so it makes a big difference. If you answered any of those ways, would be okay. And on the exam last year, it's all 3.
If you're trying to find a p-value, would you find the tail area of one side of one tail, or would you find it for both?
Right. So in this type of hypothesis testing problem, for instance, that we did, that's the confidence interval 1. The previous page. So this was a hypothesis testing, and we got a z-value. You know, so you do null hypothesis of 1/2, or sample proportion, and then the standard error is this part. So we get a z-value of 8. You would do that no matter what you're going to do. And then if you're testing, you can compare it to a z-value like 1.645. This one was phrased as one-sided. Right? Okay. So kind of. So if you had a null hypothesis that p equals 1/2 versus the alternative that p is greater than 1/2, and you get a z-value, if we're doing a significance level, it's 5% significance level, kind of what we do have for 95% confidence. Right? And you get a certain z statistic that you compute. If it's one-sided, you're looking at a normal distribution, and that has 5% up here. And that's, like 1.625. So hypothetically, not connected to that problem, because that 8 is way off the charts. If you've got a z-statistic of 1.87, right, just to put a number there, right, a p-value would be the probability you're greater than 1.87. 1.87. And we would look that up in the normal table. On the exam, I'll give you a copy of the normal table and a copy of the t-table. So we'll be able to look at those two things. So here's this version of the normal table, right? The A column. And it's only really kind of half the A column. But so 1.87, if I looked at that, has 0.9693. So the chance that a random normal is less than 1.87 is 0.9693. The probability that a normal is less than 1.87 is 0.9693. And so this tail area above that, the p-value, is going to be 1 minus that. So 0.0307. So far, significance level is 5%, p-value is smaller. So most of the tests you can compute either the z-statistic and compare it to the z-cutoff, or actually calculate that tail area. If it's phrased as two-sided, I would double that, but yeah.
Yeah.
Okay. So instead, you say that it's p equals 1.5 versus and you don't really know how it's going to go positive or negative. So maybe you have to change the color, or you just kind of change the background picture on your ad. So you're not sure which one's more desirable, or if there's any difference. And so you say you've still got a z-statistic of 1.87. The probability that a normal is greater than 1.87 is still at 0.0307 value, but because of the two-sided, I double it for the p-value. So on the exam, you can do either one, and you'll get the credit as long as you do it consistently. If you write a two-sided alternative, double the thing for the p-value. If you write one-sided, you can just get one tail and evaluate it that way. So that's the logic that we do. Yeah.
So in like this problem, how did you just like change it from like a one tail to a two tail? Like how did?
Well, so it's in the phrasing of it. This is the one-sided alternative. You're only interested in that one side. And so that would be clearly stated that, arguing it that way, that we think that this one, in that context, was a change from black and white to color, and the color getting a better response. So if you're sure, it's looking in that one direction, you think that the benefit would be translated into a probability greater than 1/2. And this one is just saying, is there any difference at all? Two-sided alternative. The one-sided versus two-sided, is in practice that translates into something that you'll pay attention to. It's kind of the second order of concern. The first, setting up a hypothesis, getting a statistic, figuring out what distribution to compare it to, and then, if it's a big z-value or very small z-value, you reject. And so kind of gave that. So it's part of it, but it's not. You can do a lot, even if that's a little bit fuzzy, and still get 1 or 2 points. Any other? Well, sure. So if you look at some of the study problems and the solutions, that we've had, a few different tests, a few different procedures, confidence interval hypothesis tests. They've either been about means or proportions, right? And they've either been one sample or we do too much with 2 sample. In this class so far, yeah, we did, right? two sample for means of proportions. So if you looked at things here, you know, one challenge is once you read some of these problems, figuring out what are the keywords that kind of help you, you know, when it was about one proportion, there's one sample size, it's either an X, like count, the number of successes, or maybe a sample proportion, maybe it's like this. And then there's, you know, a confidence interval, or a confidence test, or that sample size that we talked about. If it's two proportions, you have two independent samples, and you're looking at proportions, then there has to be the sample size for both of them. There's a counts for those two, or maybe, you know, a proportion. And then kind of a confidence interval or hypothesis test for those. There are sample size formulas for this one too, but we haven't really done those. So that wasn't really asked on the last one, but on the other practice materials. These were some of the other study materials. This first question, I'm talking about averages instead of deviations. That's not going to be proportions. And the second one was kind of the same thing. This one, out of 678 federal civil trials, originally tried in front of a judge and then appealed, 139 were reversed. So that's, N is there, and our count X is there. So our P hat is going to be the 139 over 678. I think that's 0.205. if I remember correctly. Yeah. So that one is of that type. So either than a confidence interval hypothesis that's based on one proportion. Is there a good example of two proportions that's in there? Shared data. So you'd almost have to have another sample to get an example. Yes?
Would you be able to write out like some of the formulas for like confidence intervals and the hypothesis tests?
Yeah. I mean, so in these cases, right, so the confidence interval has P hat plus or minus the normal value, P hat, 1 minus P hat. Right over here is our confidence interval. And then if for the hypothesis testing, we set up a null hypothesis. And we're going to compare our sample proportion to whatever that null value is. And we have a P times 1 minus P over N in the denominator. But we use the null value to get the Z statistic. And we reject the null hypothesis if the Z is extreme. One way of doing that is doing the absolute value of it. Either the positive or negative side. If that's greater than 1.96, would be our usual cutoff. Right, then we reject the null hypothesis because P hat's too far. And then we did the sample size formula here. We get 1.96 squared times P times 1 minus P over the margin squared ends up being that sample size for getting a certain level of accuracy. the two sample ones we can write on the next page. Yes?
Is it always 1.96, or is that just when it's 95%?
95%.
Okay.
Yeah. And so I'll primarily ask you about 95% in computing for a question. There might be some interpretation, right? So if you have a 99% interval, what happens to it? Right? You make it wider. That's not necessarily worse. There's more certainty of covering, right? You make it wider to get clear coverage, and that's just the price you pay. So there'll be a little bit of interpretation of that, but primarily the computing with that. Yeah.
What was the formula for a t-statistic?
So the t-statistic we'll do, there's two proportions. Let's do that one first to get it kind of. So for two proportions, so 95% confidence interval for P1 minus P2, it's at the sample difference. We have 1 minus 2. 95% we still use normal for the proportions. And there's a variance from the first estimator, adds in there for that, plus the variance of the second estimator. The variance and square root of all that. And so that's the confidence interval. Kind of looks like the other one, right, for one sample, except you add the two sample variances together. And then the hypothesis test, one, has these being equal versus, say, not being equal. The one kind of, when it's two sample proportions, it would have to tell you about like federal civil trials as one group of trials, and then it would have to tell you about kind of non-federal civil trials or federal criminal trials or something. You'd have to have two groups and then two proportions in there, a little bit more. In this, we calculate what would be our estimate of the proportion if this is really true. So x1 plus x2 over n1 plus n2. Kind of combined proportions. And then our statistic, we're going to take the difference of the sample proportions, right? If they're equal, that should be close to 0. And then divide by the standard error. So it looks like this formula, except instead of the separate P1 and P2 hats, we put in the combined version. And so it's often written as P hat, 1 minus P hat. And then there's a 1 over n1. And then you'd have P hat, 1 minus P hat over n2. So you can factor that out. And we reject the null hypothesis at a 5% significance level if that's bigger than, for the absolute value that is bigger than 1.96. Level if the z value is greater than 1.96, bigger than 1.96, or the z value is less than negative 1.96. It's out in the tails of the normal, kind of unusual. So those are the formulas for the two proportions. Did you have a question?
Yeah. How is it different from the pooled statistic?
So when we had, there was two sample things for mean, right? So this would be for count data. So for instance, if we had if we had 678 federal trials and 139 were overturned, that's a rate of 0.205. We'd have to have a second group of trials to compare it to, right? So maybe we have 520, and these are, criminal trials instead of civil, and a certain number of them are, say, of those that are, say 520 are appealed, let's say 20% of 100, let's say that 90 are overturned. So you'd have to calculate a second proportion for this one. Right? And then do this procedure. If you're doing a hypothesis test, you know, the null hypothesis says that these have the same rate. So then you would, you know, calculate a composite there. Right? The other way where something was pooled was these two sample t-tests. Right?
So is it C is for binomial proportions and T is for means? Okay.
Yep. It probably seems a little bit arbitrary, but there's some probability arguments about limits that are in play. So the limiting distribution of a binomial is this normal in a certain way, and so we use normal. But we know things about the quantitative measurements are in fact normal, then we divide by standard deviation, and that's where we get that extra T. So if we look at, we're interested in means. So this would be quantitative. So if there's something that describes the problem, like the, you know, the size of something, or the weight of something, or the length of something, or a certain quantitative measurement, right? So in like the first problem on the practice material, go back up to that. So this Mississippi Department of Transportation has a van-mounted video technology to collect data on the number of cracks in two-lane highways so they can drive along and count it, right? And so they found an average of 2.10 cracks with a standard deviation of 1.05. They did this in 8 sections. So because it's talking about the average and standard deviation, it's going to be quantitative. So in this, there's n equals 8. The average of these 8 x bar is 0.21. And then the standard deviation s is 1.05. And there's going to be this safety recommendation of 0.1. That would be kind of this use of 0. It's going to be an average of 0.1 there. That could be used in hypothesis testing. There's make a confidence interval. Does it include 0.1 or is it outside of it? Right, so that's the type of language. It's going to give you a sample size, an average, and standard deviation, and then you're dealing with T and means. Right? So you have a sample size, an X bar, an S. Right? We use a T distribution. This one has n-1 degrees of freedom. And our T table, Rosner's T table, has these percentages right up here. And so for 95% confidence interval, we use this one. It's not exactly 95%, because we got to get 2.5% on either side. But that had 8 sections, n equals 8. So degrees of freedom is 7. So we would want to look up like that value as a T cutoff. Yeah.
Wouldn't this be one-sided because you're looking at that there are more cracks than CQC?
You could do it one-sided, and I guess the hypothesis that's answered there is phrased that way. So if you wanted to do it one-sided, you would look at this 95% value a little fast. But I think I'll phrase the confidence interval as two-sided. If you want to do that for this, you can always divide it in half. So we look up 975, right? So that'd be 95% confidence interval, two-sided. So the formula is X bar plus or minus the T value. And then S over For the one sample test about means, there's a sample size formula as well. We can figure out approximately how many subjects to use to get a certain accuracy. So if the margin, this bar plus or minus the margin of error, that plus or minus amount margin is this. Well, what's done in practice really is just for planning purposes, start out with the normal, because you don't know, if you're choosing in, you don't know which t to use exactly. So use the normal value there. This sigma could represent the actual standard deviation, but more likely it's a guess. Maybe it's the pilot program's one, maybe it's the value observed last year. So some reasonable thing to use there in planning. If you square both sides of this, sigma squared over n, and then you can solve that n is the z squared, sigma squared over the m squared. So if sigma, what did it say in that problem? It said the standard deviation was about 0.1. Suppose it is 0.1, and we want the margin of error of, well, it has to be pretty small. Kind of plus or minus, 0.02 cracks per 50. That's pretty precise. I chose that little tiny, I want a really narrow interval in there. 95% confidence interval, we're going to use the 1.96 value. So our sample size, if we wanted that level of accuracy, that would be the 1.96 squared, 0.1 squared, that's what I'm using as the standard deviation, 0.02 squared. It's about 100. Might not be exactly. 0.2, 1.1 over 0.2 is about 5. The squared, that's 25. And that's about 2. 2 squared is 4, so 4. It's about 100. Maybe a little less. Yeah.
So, just for clarification, the S in this problem, is that, yeah, right, and the M equals, so this, yeah.
So this one is the standard deviation.
That is the standard deviation?
Sample. Sample standard deviation, yeah. So in that problem, it says of those 8, the average was this, and the standard deviation is this. So it's based on those 8, because it's the sample standard deviation. The standard error, you got to divide by the square root of n, because the x bar is more accurate than the individual measurement. So that's the one sample. The 2 sample version are going to be 2 sample sizes, 2 averages, 2 standard deviations. So it's at least a couple sentences. Get that right. 2 samples, N1, X1, S1, N2, R2, 2. And I prefer the one where we pool. So take S1 squared, N1 minus 1, plus S2 squared, N2 minus 1, over the sum of those 2 degrees of freedom. And the square root of all that to get back standard deviation. Degrees of freedom you use for this one, 1 plus 2 minus 2, the same as that denominator there. And so then a 95% confidence interval for the average difference. So for the symbols, U1 minus B2, the difference between the population averages. It's centered at the sample difference, x bar 1 minus x bar 2, plus or minus a t-value. So whatever that degrees of freedom is, 0.975. And then, instead of S over just the square root of n, there's the 2 sample sizes right there. 1 plus n1 plus 1 over n2. And those go inside of there. 1 over n1 plus 1 over n2. And that's the confidence interval, that's where that pooling comes in. For a hypothesis test, you divide x1 minus x bar 2 by that standard error, and that's your key statistics. So the two formulas are crucial. You get to have one piece of paper, so you can write this down. You can write numerical examples. You can write clues to yourself to think about: how do I know it's one sample versus two? How do I know it's binomial, proportions versus that? As you're answering the problems, you can label the different things that are in there, what's the sample sizes, and things like that. So, the study material, that was one. So let's see, was there? That's proportions. This one. 28, 19 older adults. Average net size 14.6. Standard deviation of 10. So that's a one sample problem again. This one, so 15 is the hypothesized value there. This one, right, study of reading comprehension, 3 methods of instruction, test scores were compared. So this table records the averages and standard deviations of the test scores. So 22 students were given this basal reading instruction, or DRT, or STRAT. 3 names are different. Sample sizes, average scores, and standard deviations. So it says concentrate only on 2 of these, basal and STRAT. Compute a pooled standard deviation, so it asks you to do that kind of as a step along the way. And then do a test, or you do a confidence interval for are these similar or not. This, several averages and standard deviations, so you could do 1 sample procedure for one of them, or 2 sample procedures for a pair of them. Before the course is done, we'll do analysis of variance where we can handle all 3 all at once, but that's for another day. The hypothesis test version of this is mu1 equal to mu2 versus mu1 not equal to mu2. So this one is the same average versus not. By the t statistic that we calculate is x bar 1 minus x bar 2. And divided by the standard error, and that's this same formula. S to P 1 over N1. And you compare that to the t distribution with certain degrees of freedom. Degrees of freedom are N1 less than 2 minus 2. And so if it's big, right, bigger than the 0.975 cutoff value, you're going to reject the null hypothesis. So if our t statistic, I'll write the absolute value of that one. That means if it's bigger than or that, or bigger, very much smaller than the negative one. If that's greater than the t 0.975 cutoff with that certain degrees of freedom, if it's extreme like that, then you reject the null hypothesis. And rejecting the null hypothesis means that you've concluded that the means are different. Yes?
What does the SP stand for?
The SP is this pooled one, the pooled version of the standard deviation, this one.
Oh, okay.
So there's a couple ways of doing this test. One would be to have the different standard deviations in the 2 groups, but the standard deviations are the same. It makes sense to do a composite estimate to be more precise. You could use a bigger degree of freedom, which is good.
Can you scroll down a little bit?
Yeah. So let's see. There's one. Just did that with the solution, so we'll look at that shortly. if you go to these, solutions, practice problem solutions. So set number 7. I'll get to that. There goes the card. What's that? Okay. Try that. That's blank. Huh. Is it blank on the website?
Is it the practice test or is the?
This is the practice solutions. Or the,
I don't think so.
I don't think so, it's just a quirky thing. So this is the goops. You know, I think that, I'm just, every once in a while there's a hiccup with the network connection and kind of cuts things off, so let me go back. Oops, on that page. The study solution should be posted. So yeah, they're there. So number 7. So these were the 2 Basel and Stratton teaching methods, both 22 averages, standard deviations, the pooled one, the SOP. These are standard deviations, so we square them. This is actually just like a direct average of the 2.97 squared and 3.34 because the sample size is the same. So it comes up to be 3.16. So it's kind of between those two. Have a good consensus. These are the, I use B and S for Basel and Strat. You can use 1 or 2, you can make it specific, whatever's convenient. You could write these equal averages, same averages, no difference. Different averages, you can write it in words. Here's the statistic. We get a value of 1.43. Degrees of freedom would be 42. And let's see if we can have our T-tables look like there. Oops. Oh, everything cut out. Funny. Let's start that again. Okay. So the T-tables, there it is. So 42 degrees of freedom is down here. It's kind of just beyond 40. If we're doing a level, a 5% test, half of that is 0.025. So we look at the same thing, same column we would for 95% confidence interval. And that one, going down to about 40 is about 2.02 to 2.01, something like that. But our test statistic was 1.43. Right? It's not nearly as extreme. Right? We would need to get above 2 to reject. But we got 1.43. So go back to, so we got T statistic value of 1.43. We would need about 2.02, something like that, to reject. Because our statistic is smaller, we don't reject. So the evidence doesn't really prove that those are different. Only 22 students in each group. There might be a couple point difference on that scores, but it's not statistically significant. It might be encouraging, might warrant a bigger study, 60, 120 students or something like that, but it doesn't quite prove it. With you did a confidence interval, you'd have to do that same pooling thing. And then it's an average difference, plus or minus a t-value, which is about 2.02, S the p, the sample sizes, and it came out to be a negative 0.85 up to about 0.26. So it straddles 0, so average 0 is no difference. All right, that type of problem. So that's the primary formulas for hypothesis confidence intervals. The challenge is figuring out which problem it is and using it correctly, that you can write down the formulas, words, interpretation, numerical examples. Be ready. Any other questions about it? So, I encourage you to write out the formula sheet. Try to go through this, some of the maybe some of the past homework problems independently. You can do it all. to you on this. A few students were going to hand in the last homework. And take that. All right, we'll do it.
Take down and you're like, oh, I did something.
Go ahead. No, I don't think so.
You good?
Why don't you try to recess it? And I'll double check on this. All right.
I'm just struggling with the last homework.
Okay.
I'm just kinda-
Have you done parts of it?
Yeah, I keep trying.
Okay.
I don't know if I'm getting anywhere, but like maybe today helped a little bit. I
Okay.
think I'm struggling with the finding the like the
T value or something?
yeah, kind of. But just like watching that, and now I can watch it back too. Just
Okay.
I think can I try again?
Yeah, so try it a little bit more.
Yeah.
I'll probably post them later, but, you know, try to write up what you can.
Okay. I'm sorry about that.
No, that's, you know, we dropped the lowest homework score, so, you know,
Okay.
in the scope of things, you'll still can get most of
All right, thank you.
the homework points, but, you know, it's a matter of understanding. And so
Yeah.
the fact that you're working to understand it is good.
Yeah.
And so keep working at it, and, you know, if you write some things up, kind of write up, you know, before looking at the solutions, what you're, you know, doing.
Yep.
You could either bring it in, you know, get it to me Tuesday, or maybe you can even bring it Wednesday
Okay.
at the exam. I'll probably take off a couple points just because of the.
Yeah, no, I
scope,
understand.
Things like that.
Absolutely.
But, yeah, no, I think that's good study material for the
Yeah.
exam.
All right, thank you.
Yeah, and I'll post solutions, so you can, I do want you to look at the solutions before the exam.
Yep.
So that you are ready for that part of it.
Will you be in your office tomorrow?
Yes.
Okay. All
I'll
right.
do that most today, so.
All right, thank you.
Yep.
See you then.